Hello, today we'll be covering coulombs, charges, and point charges. Before we begin, I think it's important to talk about what is charge. Well, charge comes from electrons, which have a negative charge, and protons, which have a positive charge. To measure charge, we have coulombs, as well as the elementary charge, typically denoted as Q. The elementary charge is the charge in one electron or one proton, the magnitude of that charge. Again, electrons are negative and protons are positive. The elementary charge of any proton or electron is 1.6 e to the negative 19th coulombs. Coulombs is a more typical unit of charge. Using this, we know that a coulomb of charge is the charge of 6.24 e to the 18th electrons or protons. Let's take carbon, for example. Carbon's atomic number is 6, which means there are 6 protons and 6 electrons present in every atom per atom. However, typically when we're talking about chemistry, we're talking about moles. And a mole of anything is simply Avogadro's number, 6.02 e to the 23rd particles of anything. In this case, 6.02 e to the 23rd atoms of carbon. So if a question were posed, what is the magnitude of charge of every electron in a mole of carbon, we could simply say there are 6 atoms, 6 electrons per atom of carbon. There are 6.02 e to the 23rd atoms per mole, and the elementary charge, as we said earlier, is negative 1.6 e to the negative 19th coulombs. This gives us an answer that in 1 mole of carbon, there is 578,000 about coulombs of charge in 1 mole of carbon. A second kind of charge is static charge. Static charge is simply charge that is static, or stays in place. Here we have a negatively charged glass rod attracting the positively charged charges in this ball. We can think of negative and positive charges like north and south ends of a magnet. As you know, north and south ends of a magnet will experience an attractive force, and in the same way, negative and positive charges will experience an attractive force. If we look over here, the negative charges are being repelled by the negative charges in the rod. This is similar to if 2 north magnet ends were near each other, and they also would experience a repulsive force. A fun lab to do if you ever have free time. Take a balloon, rub it on your head until it builds up a significant static charge, and then allow a gentle stream of water to pass by the balloon. It won't pass straight down. You might notice it will come and arc closer to the balloon. This is due to the fact that water, H2O, is a polar molecule. This means that oxygen has a partial negative and hydrogen has a partial positive charge. So regardless of the charge present on the balloon, let's say it was positive, for example, we could experience something like this. If the balloon was positive, the negative ends, again, the oxygen, would be attracted to the positive charge on the balloon. By being attracted to the positive end of the water, the hydrogens would be repelled. This distance is a shorter distance than this distance. Distance is an important variable because the force of static charges is equal to a Coulombic constant, which we will discuss later, times the product of 2 charges over the radius squared. What this means is the force of attraction or repulsion between 2 points is equal to K, which we can say is 9 e to the 9th, Q, measured in coulombs, and R, the distance between the 2 points, in meters. So let's consider a scenario. Let's consider a positive charge and a negative charge, 1 meter apart. The positive charge has a charge of 1 coulomb, and the negative charge has a charge of negative 0.5 coulombs. So, before we do any math, we know that since these are opposite charges, they will attract each other. So if we want to determine the force on the negative charge that the positive charge delivers, we can simply use our equation F equals K QQ over R squared and solve. Now, this is an incredibly large number. This comes out to about 45 billion newtons. This is important because most coulombic charges you see will not be in full coulombs, instead in microcoulombs. Again, micro is simply 1 times 10 to the negative 6th. So let's consider another example. Let's consider a positive charge, a negative charge, and another negative charge. Let's say the distances here are 1 meter and 1 meter. This positive charge has a charge of 6 microcoulombs. This one has a charge of 3 microcoulombs, and this charge has a charge of 6 microcoulombs. If we were to ask what net force is being experienced by this top right negative charge, we would have to do a vector diagram of two forces. We have the attractive force present here, and the repulsive force here, as these are two negative charges, and this is a positive charge. So, if this top right charge is experiencing a repulsive force away from this negative charge, and an attractive force due to this positive charge, we know overall it should be going up and to the left in some way. Let's call this force 1, and this leftward force 2. Force 1, we just do our Coulombic constant, 99, times charge 1, which is 3 e to the negative 6th, times Q2, 6 e to the negative 6th, over the radius of 1 meter squared. Doing this math, we know that force 1 is equal to 0.162 newtons, which means these two charges are being repelled away from each other with a force of 1.62 newtons. If we were to solve for force 2, it is again our Coulombic constant, 9 E9, times the same numbers. We have a 6 microcoulomb and a 3 microcoulomb over the same radius. Now you notice I'm not putting the sign of the charges in my Q values. This isn't really important because that could tell you direction, or you can think about it conceptually. here we have an attractive force, here we have a repulsive force, so we know the net is going this way. So if we have a triangle here of force 2 and force 1, and we know those forces are equal, both about 0.162, we can do vector addition, just a squared plus b squared is c squared, to find that the net force is 0.229 newtons. And because these two charges are equal, we know that this degree is 45 degrees. Which means this charge, due to the positive charge here and the negative charge here, is experiencing a 0.229 Newton force at 45 degrees above the negative horizontal axis.